Hey, VC Calc students, this is going to be your day 55 notes. Today, we're heading into the third dimension. Today, we're going to talk about how we can extend our concepts with area and relate it to volume. Before we get into the concepts of volume, we're going to recap a little bit what we've talked about so far with area between two curves. So if you look at the examples in the diagrams below, you can see the functions outlined as the one on the left here is f2 of y. So it's x in terms of y, and this would be the same thing. This would be x equals f1 of y. So to find the area here, you can see that based on our conversation at the end of our day 54 notes, it makes sense to integrate with respect to y. So if you use your bounds along the y-axis there as the lower bound of c and the upper bound of d, this area would be much easier to calculate if you take the right curve minus the left curve and find the area that way. Because along this entire interval, the right curve is always to the right of this curve on the left. And the same would hold true for any of these other examples. If you have a graph of two equations that look like the following, it would definitely benefit you to find the area between those curves by integrating with respect to y and using the lower and upper bounds along the y-axis, which is exactly kind of what this conclusion says down here. So there are benefits to integrating with respect to x depending on what the graph looks like, but don't be afraid to integrate with respect to y. Make sure that your equations say x equals something in terms of y's, and then when you subtract the right minus the left, dy will get the area between those two curves. So if we extend that to this example below, find the area between the curves with these equations, it's probably a good hint that it's going to be a dy example if they're both set up as x equals. So what am I going to integrate to find the area between these two curves? Well, the bounds of integration would be from 0 along the y-axis to this y value of 2. So we're integrating from 0 to 2 of the curve on the right, which is y plus 2. So it's going to be y plus 2 minus the curve on the left, which is y squared. And that's a dy now. Okay. So I didn't really need the extra set of parentheses here. If we do our integration, the integral of negative y squared, I'm just going to start with that since that's the largest power, would be negative y cubed over 3. The integral of y would be plus y squared over 2. And then at the end, plus 2y. And we're going to use our upper and lower bounds of 0 and 2. Plugging in the lower bound of 0 second, it's just going to return a whole 0 there. So I don't have to worry too much about that. If I plug in the upper bound of 2, negative 2 cubed over 3 plus 2 squared over 2 plus 2 times 2 would give you negative 8/3 plus 4 over 2, which is 2 plus 4. So that's going to be a total of 6 at the end. 6 is the same thing as 18 over 3 plus the negative 8/3 is a total of 10/3. And that would be square units for area. So we can use dy, I think, pretty effectively here. If I wanted to do dx, which would mean that I would draw a vertical rectangle, we'd have to break it up into two intervals, right? So if I look at the two intervals for dx, we would have to break it up at x equals 2. Because from 0 to 2, we would be integrating the curve y equals radical x with respect to the x-axis there. And then it would be the difference in the curves radical x minus, this would be y equals x minus 2. We'd be integrating the difference of those from 2 to 4. It really wouldn't be that much more challenging, but I really do think this is nicely set up to more easily think of this as a dy example. Okay. So what I want you to do is for the next example, draw a picture, of course, because that's going to help you decide if it's dx or dy, and decide, which would be easier. And in the end, you should be able to do both techniques, but find the area bounded by y equals 1, y equals x, and y equals 1/4 of x squared. So graph those three, shade in the area that we're looking for, and then decide, is this better set up to do dy, dx? Maybe try both, see if you get the same area in the end. That could be a good challenge. But I'm going to move on, and we're going to do the one at the bottom here. Find the area above y equals 2x. And then below the curve, y equals e to the negative x squared in the first quadrant. Okay, so when I sketch my picture here, I only need a picture of the first quadrant. And what I'll tell you is that e to the negative x squared, if it's going to be below that curve, e to the negative x squared doesn't really take on a very large output for y. Because if we think about plugging in, let's say 0, e to the 0 is 1. And then we're going to get, if we plug in positive values for x, a whole bunch of negative exponents. So it's going to actually decrease from there. So if we get e to the negative x squared for y1, y2 is going to be 2x. I'm going to really shorten up my window here. I'm going to go 0 to 3 for x min and x max. That should probably be fine also for y min and y max. Because like I said, the max value that this is going to take on is going to be 1, and that's the curve that's above y equals 2x. So if I hit graph at this point, there are my two graphs, y equals 2x, the linear function. This curve is e to the negative x squared. So you get a graph that looks something like this. And then here is y equals 2x. Okay. So based on this, I think this is a nice setup for dx, right? If you draw on your rectangle to represent the area and the difference in those heights there, where it's always going to be the top curve minus the bottom curve here. So I think if we use a dx example, we would take the top curve of e to the negative x squared and subtract the bottom curve of 2x. So it's going to be the integral from, well, that's going to be something we have to talk about in a sec, but it's going to be e to the negative x squared minus 2x dx. Okay. Well, the lower bound is easy. I mean, the lower bound is 0. But what is this point right here? And it turns out that that's not really going to be a nice value, a nice point of intersection. If you calculate that point of intersection, second, trace, find the intersection. Oops, let's go to the left. The point of intersection here is at approximately 0.419. Okay, so could I use 0.419 as the upper bound here and be fine to calculate the area under the curve? The answer is yes, but you can even get a little bit more precise than rounding that value. And if we call that point A, what you can do is you can go to the home screen, so quit the graph there. And if you do x stow, which we've used the stow function for, right? We're going to store x, and you're going to do x store A, alpha A. And if you hit enter, what you're going to see is that exact point of intersection gets stored as your value of A, which I think is pretty awesome. Because now we can integrate, instead of writing 0.419 as the upper bound, I can call this A as the upper bound. And I'm going to even go one step further beyond that. I'm going to integrate from 0 to A. Since we already have these functions typed into y1 and y2, we can use this input on the calculator. The calculator will know to calculate the area between these two curves that are located in y1 and y2. So let's see how fancy we can get here with our notation and our calculator. Because we don't know how to find the antiderivative, right, of e to the negative x squared. So definitely a calculator question. It's going to be math 9, lower bound of 0, upper bound of alpha A. And then y1 and y2, if you do alpha trace, there's y1 minus alpha trace y2. With respect to x, we get 0.220. Not a lot of area there, but to 3 decimal place accuracy, 0.220 is the area between these curves. So something I want you to start focusing on is if there's not a nice point of intersection, to calculate that using your calculator intersect function and then store that as your favorite lettered variable. Okay. So store it as A, store it as whatever you'd like, and then use that as your upper bound, or it could be your lower bound of integration. And then from there, be able to calculate the area between the curves. Okay, you'll see more of that comes up like that in practice. But we're now actually up to the point in the lesson where we get to the new stuff, which is talking about volume. So at the top, it says we can use integrals to calculate volumes, similar to how we found area under a curve. But now we're going to look at this in 3 dimensions. So here's what the process would look like. We're going to take an interval from A to B. We're going to divide it into n subintervals. We've done this many, many times before, I feel like now at this point, in talking about Riemann sums, which represent areas under the curve. Okay. Then it says, look at the slice in the ith interval. So we're going to cut this into a bunch of pieces. What would happen is that the volume of the slice could be represented as A of x sub I delta x. So what I want you to think about is if you go somewhere along this volume that I've generated, and how did I generate that volume? I took this area, and you can see this little arrow here. It got rotated around the x-axis. So if you take this plane surface right here and rotate it around, hopefully it makes sense, you would get a shape that looks like this. And we're trying to calculate the volume of that shape. So the way we're going to do that is to find we're going to find the area of this piece, and we're going to multiply it by delta x, which is the thickness of that slice. So we're kind of slicing this up into a whole bunch of pieces, right? And we're going to find the area of the face here of a slice and then multiply by the thickness of that slice, which is your delta x. So that's the volume of one slice. The volume of all slices, therefore, could be the sum from I equals 1 to n of the areas of all the slices times their thickness. So now we're kind of building our case of saying, all right, the volume of all such slices can be represented with the summation. And therefore, if you take the limit as n goes to infinity of that sum, that Riemann sum becomes the definite integral from a to b of a of x dx. Now let's kind of take this one step further. If I look at these slices right here, these slices are all going to be cross sections that are circular, right? You can see the circle here. If you were to slice it in the middle, you get a little bit of a smaller circle, slice it towards this side, a little bit of a bigger circle. So you can even take this one step further and say, oh, it's the integral from a to b of pi times, well, here's my radius right here, right? Area of a circle is pi r squared. So it's going to be pi r squared dx, where dx is the thickness of that slice. And we know that the integral from a to b would represent the sum of all of those slices that we're talking about. Now, since pi is a constant very commonly in these questions, when we find volume, we're going to pull the pi to the outside and represent this as the pi times the integral from a to b of the radius squared dx. Well, how am I going to get the radius? The radius is the height along the function y equals f of x. So hopefully this connection's all starting to make some sense according to the picture, according to the development here. Okay, and these are called solids of revolution. We're taking a plane surface like this right here, and we're rotating it around, and we're resulting in a figure like this. Okay, so it's rotating a plane area about an axis in the plane. So consider y equals x from 0 to 4. We're going to rotate this area around the x-axis and then find the volume of this solid of revolution. So think about y equals radical x. From 0 to 4 would look like this, right? If this is x equals 4 at the end. Okay. So what we're going to do is we're going to take this area right here, and we're going to spin it around the x-axis. So when I do that, you're going to get a region down here. And the best way I can just start to describe this is it starts to look like, I don't know, like a ham, where if you were to slice different parts of the ham, by the time you get to the ham, and I know this is kind of an odd reference, but you would get all these circular slices of ham as you get towards the end there. So what's going to happen is you're going to get a whole bunch of volume here. And this method that we're looking at is called the disk method. So you get all these little circular disks that if you find the sum of all those volumes of each disk and add them all up, that would be the total volume here. So let's kind of think of this just in terms of the volume of one slice to get started. The volume of just that one slice would be pi r squared times the thickness delta x. So what is r in this case? Well, the radius is the height that's drawn up to our function radical x. So the radius is radical x. So therefore, the volume of one slice is pi times radical x squared delta x, which is pi x delta x, right? So if that's the volume of just one slice, then the volume of all the slices would be, using our definite integral, would be the integral from 0 to 4 of pi x dx. So like I showed you earlier, usually I'm just going to pull that pi to the outside. So it's going to be pi from 0 to 4 of x dx. So if we use our anti-power rule, this is going to be pi x squared over 2 from 0 to 4. And 0 is just going to give us an output of 0 there with that lower bound. The upper bound would be plugging in 4, so that's going to be 16 over 2, which is 8. So therefore, your volume is 8 pi. And since we're dealing with volume, now we're looking at cubic units. 8 pi units cubed would be the volume that results in taking this plane right here, this area, and spinning it around the x-axis. I'll bring in some other models for us to look at to help visualize, because sometimes the pictures can be a little bit tough to draw and represent in a two-dimensional space what the volume might look like in a three-dimensional world, okay? Last thing we're gonna do today, and of course we'll do more disk method as we get more practice here. So next time in class, we'll do some good practice problems here. The last example is kind of awesome. This might blow your mind today. It says the circle x squared plus y squared equals r squared is rotated about the x-axis to generate a sphere. Find its volume using calculus, okay? Now, the reason why it says using calculus is we already know the volume for a sphere, and if you don't remember it, you're going to think it looks really familiar by the time we're done here. So it doesn't really matter what our radius is here. We're taking the circle that's centered at the origin and we're spinning it around the x-axis. And when I do that, it's going to generate a volume. And it's going to be the volume of a sphere. So what I'm going to think of this as is if we were to just look at this in terms of the part of the circle that's just above the x-axis, this half circle here, if I were to spin this around and rotate that, we would get this resulting region down below, right? And this would generate that three-dimensional volume that we're looking at and create a sphere. So if I were to take this, spin it around the x-axis here, we're going to get what's the resulting graph of a sphere. So what we have to do is, if we're going to integrate this, we have to figure out the bounds of integration. And the other thing we have to do is, if we're going to figure out what the radius is, if I were to take a slice out of here, the radius is the height along this curve. Well, I have to figure out how do I represent that height as y in terms of x. So really quickly, let's get y alone and say y squared equals r squared minus x squared. And then we would from there say that y equals plus or minus the square root of r squared minus x squared. Now the plus or minus is the top half and the bottom half here, right? So since we're only going to integrate along the top half of this circle and then spin it around, I don't think we need the plus or minus in this case. And then we just have to think about what are the bounds that I'm going to integrate along. You have two options. If the radius length is r, you can go from negative r to positive r, and that would be fine. Or I'm going to get a little fancy on you just because this is a technique that will help in the end. If you think about just this section right here from 0 to r, and then we double it, that would get you the total area along the top here, okay? So let's choose this technique where we say, all right, let's double the integral from 0 to r of pi times the radius squared. And remember, the radius that we're looking at is this height right here. So at any given moment, if I were to slice off a piece right here, that height to the function right here is going to be radical r squared minus x squared. Now, since the radius is radical r squared minus x squared, we're going to take that radical r squared minus x squared and square it, right? It's pi r squared dx. All right. So from here, I'm going to do a couple things. I'm going to pull the pi to the outside because I like having the constant out there. From 0 to r of, well, when I square that radical, it just becomes r squared minus x squared dx. So if we're integrating with respect to x, when I go to do my integral here, I'm going to write the first term as 2 pi times, this is going to become r squared x, right? R squared is a constant, so therefore when we integrate that constant, it's going to be r squared x, then minus x cubed over 3. And we have our upper and lower bounds of r and 0. So now at this point, we're going to plug in the upper and lower bounds, start simplifying, and see what we get in the end. So we get 2 pi. If I plug in r first, r squared times r is going to be r cubed minus, plug in r here, it's going to be r cubed over 3. When I plug in the lower bound of 0 for x, it's going to be minus 0, so I don't have to write that piece. Well, r cubed minus r cubed over 3, this is 1 minus a third, so that would be 2/3 r cubed. And as soon as I write that, you might be like, start thinking, oh man, I know that where this is headed. 2 times 2/3 is 4/3 pi r cubed. That is the volume of a sphere formula. Wow. If you were in front of me right now, your jaws would be dropped to the ground, okay? So you can use calculus to generate the formula for the volume of a sphere by using this disk technique that we learned in today's lesson. So with these two examples, this was pretty generic here, right? We didn't really have definitive upper bound. We were using the general case where the upper bound was r. I promise that as we do more with volume, we will get more disk practice next time we're in class, but this I think is a good start to get you thinking about the concept today. So next time I see you, more disk method to come. Have a great rest of your day.